Right. Thanks. So young stars with ages of just a few million years are fairly rare in the solar neighborhood, and the sources that are young with well-characterized spectroscopically are rare still. And previously, the major surveys that have provided spectra of young stars came from just a handful of very well studied star forming regions, for example, Orion, Ophiuchus, Vela, Taurus, and a few others. But that is starting to change because we are currently missing all of this galactic plane that biases our measurements. But Sloan Digital Sky Survey in its fifth iteration is set on obtaining spectra of several millions of stars across all of the evolutionary stages across the entire sky. And one of the major programs within SDSS-5 is ABIS, which is a program that is dedicated to young premium sequence stars. So for this program, we have assembled a census of approximately 200,000 candidate young stars that have been selected using a variety of different techniques, such as variability, infrared access, clustering, location above the main sequence, and several others. And all of these sources are being observed with apogee, which is a high resolution near infrared spectrograph in H-band, and with BOSS, which is lower resolution, but it is optical and it covers all those wonderful use-sensitive lines. And the survey has been going on for about 2-3 years now. The first data release is going to be expected probably next summer. And just to show you a preview of what we have been able to get so far, there's already tens of thousands of young stars, several tens of thousands, covering the bulk of the galactic plane. And in the next couple of years, we're hoping to fill it up even further. So getting these spectra is one thing. We also need to get their stellar parameters. And to do that, we have developed a neural network that is able to predict temperatures, surface gravities, and metallicities for all of the stars observed by SDSS, not just the pre-main sequence stars, but also main sequence, brown dwarfs, white dwarfs, red giants, OB stars, and everything in between. This is all done in a self-consistent way without any model grids. But what this means for the pre-main sequence stars specifically is that surface gravity is a parameter that is very sensitive towards age, because as stars get contract to the main sequence, their surface gravity increases as they shrink down. And all of these sources, they're color-coded by the ages estimated photometrically. And these lines, if you can see them, they are missed isochrones of temperature and surface gravities of a few select age cuts. And as you can see, what we're getting spectroscopically with log G is in perfect agreement with photometric ages. So we are starting to move towards a point where we no longer need to necessarily rely on photometry to get ages. And by the way, this works on BOSS spectra, this works on most spectra. We are currently trying to expand it towards Gaia, XP spectra, and we are able to get surface gravities for young stars from low resolution Gaia XP spectra. So, but that is still in the works. So with these stellar parameters, let's take a look at actual spectra. Here's an example of a typical accreting young star. We have strong H alpha line, a variety of different other accretion lines, emission lines, slight excess in UV. And here we have our beautiful lithium line. Now, BOSS is a fairly low resolution spectrograph. It has R of only around 2000. So there's not a whole lot of points to cover this line. So measuring equivalent widths of lithium can actually be something of a challenge in spectrographs in this low resolution. We've tried a couple of different things, Gaussian fitting, template subtraction, they don't really work all that well. What we found to be the most effective is actually measuring equivalent widths by hand. Just defining the continuum, integrating on the curve to get the equivalent width. Obviously, it's not feasible to do for tens of thousands, hundreds of thousands of stars. But what we have done is we've picked only a few thousands of sources, measured equivalent widths for lithium and several other use-sensitive lines, and built a neural network that will be able to estimate equivalent widths for the entire sample as a whole. And by the way, this work was led by undergraduate students currently rising senior at Vanderbilt, Rat Tawad. Please check out his poster on his current work, poster number 65, on Bailing in Boston. And so after we have been able to develop this model, we have been able to derive all of these equivalent widths for all of the stars that have been observed by SDSS. And here are the equivalent widths from H alpha. Here are all the beautiful disk-bearing stars with strong emission lines. Here are the weak-line K-Tauri stars. But these weak-line K-Tauri stars have significantly stronger H alpha than the field stars that are not young, because it's primarily that emission is primarily due to use magnetic activity, and the emission strength decreases as the magnetic fields get weaker with age. And here we have the lithium in all of the young stars, typical equivalent width of approximately half an angstrom, dropping towards the pool of stars, dropping toward high stars. And this, again, these spectra are fairly low resolution, so we do have pretty high uncertainties in the individual measurements, but together they do tend to have a fairly good correlation with existing lithium measurements for some of the stars that have been observed in the past. And so even so, each individual measurement you may not necessarily trust quite as much. With tens of thousands of stars, it's possible to beat down the noise quite significantly. So let's take a look at how lithium evolves across different temperature and age bands. Here, we're showing various panels from approximately 1 million years to approximately 10 million years. The red line was the Jeffreys model for these age ranges. The yellow points are the actual measurements that we have. The black points are the typical value in each temperature and age band. And we've tried to build a fancier model. Fancier model didn't work, so we just left with a polynomial fitting to these black points. And what we find is that there is actually a pretty continuous decrease in lithium equivalent widths from the youngest ages, from approximately 1 million years to 3 million years. There is some slight drop, but after 3 million years until about 10 million years, everything kind of stalls for a little while. And after 10 million years, it begins to decrease even further as we get towards older ages from lithium depletion. So this is why having such large surveys is nice, because it's possible to see all of these details that may not so be seen with only one or two clusters. And also, again, these are fairly low resolution spectra. Here, these black error bars show the typical scatter in each temperature and age band, and this gray error bar shows a typical uncertainty in the measurements. And so we can compare the scatter to the uncertainty. And what we find is at the hotter temperatures, the scatter is almost perfectly reproduced by the uncertainties. But at the cooler ages, at cooler temperatures, at every single age range, the scatter begins to explode exponentially. And so, as Lyra has mentioned, magnetic fields could significantly affect lithium. These stars are fully magnetic. Therefore, perhaps we may not necessarily be able to estimate ages quite as easily from the stars. So to summarize, huge catalog of measurements. The first data release should be available next year. Some of the preview from lithium from the most surveys are already published. And there's even more to come in the future. Thank you. Uh-huh. Oh yeah. Yeah, so the same pipelines, BOSS is very similar to Lamont. It's very almost identical, only slightly narrow wavelength range. Even the pipelines that process them are very similar. So when we were building the pipelines for BOSS spectrograph, we've also extended the same pipelines to Lamot's data. So the temperature, surface gravity, melicities, we've ran them through on the Lamot spectra as well, and the line forest we also ran on Lamot's data. In the paper, we have included the measurements of only the pre-main sequence sources, but if you're interested in the older stars, we also have measurements of cool input for them as well.